Okay, nice. So hi, I'm Simon Sir, also known as Immersion, and I'm going to talk about libliftoff. So yeah, libliftoff's goals is to take advantage of KMS planes. So I'll first explain what is a KMS hardware plane. Then I explain what is libliftoff and what's the current status of the library. And then we'll see what the next steps are. So this talk will be is designed to for mere mortals to understand what the libliftoff is. So if there are experts in the room, maybe it will be a little boring at the beginning, but yeah. So first, yeah, what's a hardware plane? So first, it has nothing to do with actual planes. So it's hardware features in GPUs. So before getting into hardware planes, let's just see how we get a frame on screen. How do we show something on screen? So basically, there's a user space program that wants to show something on screen. So it has a frame. So here's a typical screen with a terminal and a few windows. So it talks to the kernel. It's a kernel interface called KMS. So it submits a frame to KMS. KMS then talks to the driver. So you have a different driver depending on the GPU vendor. So for Intel it's i9-15. For AMD, it's AMD GPU. And each driver will program the hardware to display the frame on screen. So one important thing is that since, I don't know, a few years, we have a new API to do this, which is called the atomic API. So submitting a frame is now atomic, so you don't have a partial frame on screen. You don't have tearing and things like this. So it's much better than before. With the legacy API, you could have corrupted frames. Not great. So the client is typically called a compositor because it will take a few windows. So a terminal window, a calculator window, a document window here, and it will draw all of these windows into a large buffer. So it will actually perform a copy, and then it will submit the final frame buffer to KMS. So nowadays, this is performed using OpenGL. So planes basically allows the compositor to not to copy and not to use OpenGL at all, but to submit directly the client buffers to KMS. So here, the compositor will submit 3 buffers in one step, in one atomic commit, with some metadata. So for instance, it says terminal window is on the top left, the calculator window is on the bottom right. So you just submit this full state to KMS, and the hardware will perform the composition directly in the scan-out engine. So you don't copy anymore. And you have an API to set properties and all of these windows, like the position. So why do we want to use planes? So it's zero copy, as I've said. So sometimes it's very important because some hardware needs a lot of time to perform copies, depending on the location and buffers and everything. For instance, ARM GPUs, it makes a big difference. You also get lower latency if you don't do a copy, because you don't need to wait until the copy is over to submit the frame to KMS. And it also improves power consumption, because when you use planes, the render engine can go to sleep. So the part of the GPU that is used for OpenGL is not used anymore and is not using battery. Only the scan-out engine, which is sending frames to the screen, is still awake. But planes come with some downsides too. They are very hard, so pretty hard to set up and use, especially when you don't control the buffer, especially if buffers come from clients. So right now, compositors don't really support planes. There's one exception. Western supports plane pretty well. But apart from that, everybody just always composites the whole image. So one little exception is the cursor plane. So when I move my cursor here, most compositors are able to put it in a plane, a special plane called the cursor plane. But that's the only thing compositors are able to use, except Western. So one other issue with planes is that they are, so I said planes are hard to use, and that's because they come with some constraints. So for instance, here are the planes I have on my Intel machine. I have 3 planes. The first plane here is able to display buffers with only a few formats. So for instance, it can do C8, RGB 565, and all of this in the list. The second plane can do a different set of formats with YUV formats. And the last plane is only able to do ARGB 888. So you can see that I only have a limited number of planes with a limited number of formats supported on each plane. So for instance, let's take an example with these 3 windows and the 3 planes I have. So for instance, if this window is using ARGB, this window XRGB, this window XRGB, then I can put everything into plane and everything's fine. But if the first window is using XRGB, then I can't do that, and I can't use planes. So planes come with a large number of constraints. So we said number of frames, formats, but you can, there are also some constraints on the buffer size, some constraints on the Z position, so which plane is over which other plane. So for instance, on my machine, the first plane would be under the second plane, which is under the last plane. And I can change that. Some hardware is able to change the Z position. There are also some bandwidth constraints. So if I use windows that are too large, I can't put them into planes. And a lot of weird stuff. For instance, on my YUV plane, if I want to, on my second plane, if I want to display YUV buffer, the position must be even, I think. And if it's the position is odd, the position coordinates are odd, then it doesn't work. That's Intel specific, of course, and every vendor has some vendor-specific constraints like this. So yeah, that's a mess. And the only way we know whether some combination will work or not is to perform what we call an atomic test-only commit. So we basically say, hey, I want to display this window on this plane, this other window on this other plane, and we ask the kernel, we ask KMS, will this work? And KMS says yes or no, but we don't know why. So yeah, that's how we use planes, basically. So now we can dive into what's libliftoff. So the goal of libliftoff is to make it easier to use hardware planes. One goal is also to not abstract too much, to be as thin as possible, a thin layer of abstraction, to don't get into in the way of the compositor. So if the compositor wants to use special hardware features, or so we want to let the composer customize a lot how it uses planes. So we had a workshop at XDC last year, and so this presentation is basically what we've done so far and what are the next steps. So the basic idea behind libliftoff is to expose some layers. So layers are virtual planes. They are the same as planes. You can set the position, you can set the buffer, you can set a bunch of properties in them, but they don't have any constraint. So you have as many layers as you want, and you can set any property in them. It's fine. So basically, compositors can use layers just like they would use planes. And then libliftoff will see which layers the compositor has set up, and then try to map them into planes. So yeah, libliftoff performs the layer to plane mapping. So let's see a very basic example. So it's a pretty simple API. So for each GPU, you can create a libliftoff device. And then for each device, you have a bunch of outputs. You can create an output, a libliftoff output. And then you can create as many layers as you want. Here I create a layer. I set the frame buffer ID. I can set the position. I can set the scaling method and a bunch of stuff like this. So these are just standard plane properties. Yeah, probably a real-world example will set up more layers like this. And then the compositor can just call this function, liftOff output apply. And this will fill an atomic commit with all the planes state. And the compositor can just perform the atomic commit, so send all the properties to the kernel and to display a new frame, and that's all. So all the compositor has to do is set up a bunch of layers, and then this was done. This is like before. Like this doesn't change. Compositor were already doing that before. So one small problem with this is that sometimes some window cannot make it into a plane. So we've seen before that if this uses XRGB, then I need to fall back to composition. But I don't need to do that for, so in this example, if these two can be put into a plane, we must fall back to composition to copy them into a large frame buffer like before with OpenGL. And if this makes it into a plane, then we don't need to copy it. So this is a mixed mode where we use planes for some windows, but not for all of them. So the way it works is that, so yeah, one important thing before seeing how we can manage this situation is that libliftoff doesn't perform any composition. So the compositor is still responsible for using OpenGL and copy window buffers into the larger buffer. So basically, compositors will have this larger frame buffer. They need to mark it to tell libliftoff this is the composition layer. So please, if you need to fall back to composition for some windows, please use this layer to indicate I need to perform some copies and this. So there's a function for this, and then compositors need to, after performing calling the function that performs the mapping, libliftoff output apply, compositors need to check each layer, and if the layer couldn't be put into plane, then the compositor needs to copy it with OpenGL. So The current status is that so the layer to plane mapping works. We have some support for collision detection. So for instance, if you have two windows that don't collide, then you don't care whether a plane is on top of the other or not. You can just put the two windows into planes and you don't care about the relative position. We have support for basic incremental updates. So if you only update the buffer property and you don't update any other property, we can reuse the previous mapping we had. We don't need to recompute the whole thing. And one important item is that we have some unit tests. I feel these unit tests are pretty important because it's very easy to change a bit of the algorithm and then get it wrong, and it's very hard to debug. So we have a mock libdarm library which fakes some hardware planes and checks that libliftoff does the right thing. I also focused on doing some field testing, so making sure that in the real world it makes sense to do this, to do what libliftoff does. So the first thing I've done is starting a glider, which is an experimental compositor using libliftoff. This is just to prove that the API is fine and that with real clients, with real windows, it works. So the goal, I'm working on WLRoots, which is a Wayland compositor library, and I'm working on making it ready for libliftoff. So we need to add a bunch of new APIs and refactor some things. There's also Valve is working on a compositor called GameScope for the SteamOS distribution, and it will use libliftoff as well. So that's pretty cool to have some other people trying it out. So with Glider, I've performed some very, very early benchmarks. So we can see here that so the compositor is the first item. This test was done by using a very simple client that just was a gradient in a 250 per 250 pixels buffer, so a pretty small buffer. And we can see that, yeah, the power estimate is like, yeah, it's pretty good. We use less power than before, so that's a good sign. So, but yeah, again, we need to like take a step back when reading these numbers, because when falling back to when using composition, there was no optimization like damage tracking or anything like this. So when doing composition, the whole screen buffer was copied each time. And when using planes, there are absolutely no copy whatsoever. So yeah, that's pretty good, but maybe real-world scenarios will be like not as optimistic as this, and clients will probably use a lot more power, of course. So yeah, what's next? So I have a bunch of short-term goals. The first one is to perform more benchmarks. One issue is that when libliftoff has a bunch of layers on it to try to map as many layers as possible to planes, the algorithms takes quite a long time because we need to perform a lot of atomic commits. So we need to take a layer, put it into a plane, and ask the kernel, will this work? If it does work, take the second layer, try to put it in the plane, ask the kernel again, is this fine? So this takes quite a long time, depending on the hardware configuration. So I have some ideas to try to find the best layer to plane mapping a little faster. we need to test more hardware and see how it behaves. But one important thing is that the incremental update saves a lot of time. So most of the time, you only change the buffer. You don't really change the position of the windows a lot. So you just update the contents of the window. So incremental updates are very important to mitigate this also. So the goal here is to not miss a frame. We basically have a budget if the screen refresh rate is 60 hertz, then we have 16 milliseconds to do everything, to do a new frame. So yeah, we need to be fast. We need also to better support so layer priority is an important thing. So if a window updates a lot, so for instance, if you have a video player, each frame will be a new one, and you will never basically reuse the previous frame. Then you really want to put it into a plane to avoid having to copy the thing. So you want to try to see which layers are updating more often than the others and put them into planes in priority. I'd also like to have better multi-output supports because right now the first output that comes will take all the planes it can take, and if you have another output, then it won't have as many planes. So we need to be fair when splitting planes across outputs, and also we need a way to migrate planes. So for instance, if I use 10 planes and one output and a new output comes in, I need to migrate planes from the first one to the other one. And it's a little bit tricky because sometimes the output are not refreshed at the same time. So for instance, if both outputs have different refresh rates, yeah, there's some synchronization issues here. I have also a bunch of long-term goals. So the first one is to have a feedback loop. So basically the idea is that right now clients allocate buffers, send it to the compositor, and the compositors need to do the copy. And so the client decides what the buffer format is. So here the client decided XRGB. But then the compositor cannot put it into a plane. So the idea of the feedback loop is to not just be sad and say, okay, I can't put the window into plane, life is terrible. The idea is just to let the to add a way for the compositor to say, okay, to say to the client, I can't put this format into a plane, but if you allocate using this different format, ARGB, then life will be better. And so the client can do it. So we need a little protocol so I'm working in Wayland, so I'm working a Wayland protocol to do this. Some kind of feedback loop to say, okay, use RGB, and the client says, okay, I'm using ARGB now. So yeah, this is work in progress. It's called DMA buff hints. One of our long-term goal is to have driver-specific plugins. So as I said, right now we have only the atomic test-only API to know if a plane combination will work. So the idea will be to have some driver-specific plugins inside libliftoff itself. So we could have logic to say, okay, on Intel, I know that this won't work, so I won't even try it. And things like this. And I know that the bandwidth limitation is this limit, so I won't try to go over it. So this would allow us to be more clever when allocating, when doing the plane mapping. And the last item, but yeah, it's for the future, is exotic configuration. Sometimes you have planes which are under the composition layer, so you need to draw a hole into the composition plane to be able to show some planes under it. So it's very, very, yeah, tricky. We'll see if it's worth it. So there are a bunch of references here, if you're interested. And thank you for your attention. Yeah, feel free to ask questions. Yeah, go on, David.
How do you know which windows to put into libliftoff? To put everything in there, or just the ones which are going to which you care about, like the games and video players?
So, can you repeat the question?
Sorry. How do you know which surfaces you should put into libliftoff? Do you put in every window that we have, or just the ones that have a high frequency? Okay, so
I'll repeat the question for people on the stream. So the question is, so this is a question from the compositor point of view. Yeah. So as a compositor, do I put every window and put it and create a libliftoff layer, or do I do something else? So yeah, the answer is basically you take every client window, you create a layer, and then if it works, if it's put into a plane, libliftoff will tell you, okay, you can put it into a plane. And if it doesn't, then you need to fall back to composition as you were doing before. Yeah.
I was wondering, is it typical for your graphic cards to have only 3 layers, or some have 4? Or...
Okay, so what's the so the question is basically how many planes do we have generally? So my Sunday Bridge laptop is pretty old and only has 3 planes, so that's not a lot. I know that newer Intel hardware has a lot more planes. I think like 7 planes or something, and some ARM GPUs basically don't have a maximum number of planes. Like you can have as many planes as you want, but you have some bandwidth limits. So they expose 10 planes, and you can try to use them, but at some point it won't work anymore. Yeah. The trend is basically we'll get more and more planes as we keep going. So that's pretty good news. Yep.
Shouldn't the heuristics be in the kernel? You talk about doing the device plugins in user space, but in my mind it would rather be in the kernel, right?
Yeah, so we've talked also about libliftoff IOCTL. So basically you set up your layers and send all your layers to the kernel, and then as the kernel, will this work, and do I need to composite anything on it? Yeah, there's been some talk about this. I think it's important here just to start with this. And then if it works, then we can discuss about maybe putting it into the kernel, or maybe having device-specific plugins. We'll discuss with the kernel developers what makes most sense. But for user space, they could just keep using this API, and it won't change. It's basically an implementation detail. So we can change how it works behind the scenes, and it won't matter a lot for user space. Yeah, the idea here was just to use the current API as it was designed, and then depending on the result of the experiment, will we continue using this API or not? We'll see. Yep.
What about traditional Xorg? Does it use any kind of feature?
So Xorg, yeah. I don't think Xorg is using hardware planes. Is it?
Old style mode setting stuff, so all the X-video stuff. All the X-video stuff from
all the
2000s.
Okay,
all
so
implemented YUV and all using all the planes there as well.
So it was able to. Yeah, but so right now, if I have Xorg GNOME session, will it use plane or not? Yeah, yeah, okay. So, yeah, okay. So legacy. So there's some legacy, and it was able to use planes at some point, but the new stuff is not able to.
and the number of planes on all winner is 74 for all winner devices.
All winner devices, 74?
74.
74! Are you kidding me?
7 for each pipeline.
For each pipeline, okay, all right.
With Intel starting from Ice Lake, you can have 30, no, sorry, it's 8 planes and then
So Ice Lake,
pipes.
8 planes,
Yeah, and then
so 8 planes per pipe, right?
yes,
So per output, okay.
and then on Tiger Lake, it's 32 all in all. Basically.
So 32 planes total, distributed across,
Same like 8 times 4.
okay. Oh, okay, so, okay. Yeah. So for, like, I think for most desktop applications, like 8 planes is pretty good already. Don't need a lot more.
So we can do like 10 more minutes of question time because Eric is a bit late, he's stuck in the bus.
Okay.
So you can go off at 10
Feel free to
more
discuss.
More questions.
Are you planning on handling transforms properly? So some planes sometimes can and can't scale, they can and can't rotate, they can only rotate to specific formats, etc., etc., etc.
Yeah.
Are we adding that as well, or is that already there?
So, so the way you do scaling is basically setting some properties on the planes, and layers are you can set any property on it. So basically, you can set the scaling properties, and it will just work. It will just try so on each plane to use it, and maybe it works, maybe not. If it doesn't work, it will ask you to fall back to composition. So it's everything. So you can set any property. So all plane features should just work, basically.
But would you optimistically set every property and then it could fail, or would you like roll back?
So you can set a property that doesn't exist, and then it will fail always.
But then you don't have feedback on which property to roll back, right?
And which
So like if you have a conservative set of properties like X and Y position in Z order, for example, which you expect to work, but then you want to go more like transform, which is less likely to work, and you have maybe 10 properties of which 4 of them you think are going to work and 6 of them, some subset of them might work. Is there
so
a way
basically the idea is that when you want to do a transform, if you can't do the transform, in any case you'll fall back to composition, right?
Right. But you
So-
don't want to. So what I'm saying is that falling back to composition, it would be a suboptimal. There's a more optimal solution that doesn't include transforms. Like maybe only one of your windows is rotated.
So what's the situation? Like, can you describe a like desktop which?
Yeah, sure. Let's say you have terminal here,
Yeah.
and the calculator here, and the calculator's 90 degrees, or it's like a picture or something that makes sense to rotate. So it's rotated. You have one rotated client and
Okay.
one non-rotated
Okay,
client.
okay.
And ideally, you can put them all in planes and then let the GPU rotate that one client for you.
Yeah, yeah.
So you might specify with the libliftoff layer, I have this one that I want to rotate, this
Yeah.
one I don't want to rotate.
Yeah, sure.
And maybe we extrapolate this for another 5 properties that are maybe some kind of exotic, like this one is YUV and this one is something else. And it fails because the GPU doesn't support rotation.
Okay.
Is the
So-
compositor expected to just peel off properties one at a time and keep trying? So it takes off the rotation and tries again.
So
and
if you
takes
want
off
to,
something else,
if you
tries
take out the rotation, then your final image won't be the same, right?
Right, but then the compositor could just rotate it in software and still use the plane for the other client that doesn't need to be rotated.
So, yeah. So basically, that's what happens. So if the rotated client can't be put into a plane, so
Because of the composition.
because so it will ask you to composite it, but the other client can be put into a plane, and that's fine.
Are there plans for multiple composition layers? So like you could composite onto a plane and then composite onto the background?
Yeah, so that's more complicated. It's planned, but it's we'll see for the future. Just doing this will already be a big win, so we'll see. Yeah, having multiple composition layers is like, yeah. Harry.
More questions?
Yeah, go on, please.
More curiosity, but since this is set, the criteria for allocating the layers to planes are very dependent on a lot of things, as I understand.
Yep.
I expect that it might very well be that you have to frequently reschedule things, as if you move windows and, for example, one coordinated was even becomes odd.
Yeah.
And I don't know what happens. So you probably have to change your allocation. And maybe at some point you didn't expect. At some point you could avoid composition, and immediately you have to start using composition.
Yeah.
I expect that this could be a problem if your composition flow is called cache is not being recently used. It could be quite slower the first time you use it.
Because you need to like boot up the run engine. Yeah, I don't know if it takes time to. We need to do more experiments. Yeah, I'm not sure. Need to ask the device, like the kernel drivers guys, to see if that would be an issue.
Issue with optimism. The district GPU might be up, but then if you use the IGPU.
Yeah, you basically don't want to use discrete GPUs for composition anyway, because if you unplug it, then you don't have anything.
Then have the external discrete GPUs.
Yeah, there's a lot of complicated issues with the layer-to-plane mapping algorithm. It's pretty annoying to, yeah.
It might also be possible to like do some guessing in advance, like if the client or the user moves their mouse cursor over the paddle bar and it looks like they're getting ready to drag, you might want to boot up that render engine.
Yeah, yeah.
Maybe the compositor could just fall back to full composition whenever something is moving.
Yeah, so in any case, if something too hairy is going on, then it will fall back to composition anyway. So, yeah. Yeah, I'm not a fan of like letting the compositor say, okay, the guy is moving the mouse under the thing, so I'm gonna do some heuristics to. Yeah, we need to do some experiments to see if it's worth it or not. Yeah, sure.
Is there any kind of mechanism, and if so, like how is it exposed in the API regarding either partial updates, like when the window doesn't need to update part of it, or when it's not clear, or things like that?
So partial updates and windows being occluded behind other windows. So partial updates for planes you don't really need to say to the GPU whether only a region. Oh, actually there is a property for this. Yes.
So, OS have their own buffers. Some of them have own buffers on the panel itself.
Yeah.
Do partial transfers to
Actually, you can set up a layer and say I only updated this region of the layer, and then the hardware some hardware will be able to make use of this. So the compositor without libliftoff already does damage tracking, so it keeps track of which parts of the screen have been updated since last frame. And then only repaints the parts that need to be repainted. So it could just like set the property and the layer, and it will be fine. And so right now I don't have any logic to not show layers that are completely occluded behind other layers, but it's a little difficult sometimes because if you have transparency, for instance, you still want to like draw the layer even if it's completely occluded behind. So the compositor will have more hints. Some clients can say, my window is completely opaque, so it's fine if you don't do anything under it. So compositors are more knowledge to do this and should already do this for OpenGL. I'll see if, yeah, I don't know if it's worth it to add this to libliftoff. Yeah, maybe in the future, we'll see. Depending on the buffer format, if it's XRGB, for instance, we know it won't have an alpha channel, so we can say it's opaque and don't do anything under it. Yeah, maybe, we'll see. Okay, yeah, sure.